You know, it's pretty wild to think that a huge piece of our clean energy future might actually be a 60-year-old technology that was first designed to go to the moon. We're talking about a power source that has worked in literally the harshest environment we know of, and now it's being re-engineered for a brand new life right here on Earth. So let's dive into the amazing story of the alkaline fuel cell. I want you to think back to the Apollo missions for a second. Yeah, the massive rockets got the astronauts off the ground, but what about when they were just coasting through the blackness of space? What was providing all the essential electricity and water for the command module? I mean, what kept the lights on, the computers humming, and the crew alive on that incredible journey to the moon? Well, the answer is the alkaline fuel cell, or AFC for short. This was one of the very first modern fuel cells ever developed, and honestly, it was the unsung hero of the Apollo missions. While the rockets were getting all the attention, the AFC was the quiet, unbelievably reliable workhorse in the background, providing not just electricity, but also the drinking water for the astronaut. So here's our game plan. We'll start with its amazing role in the space race. Then we'll pop the hood and see exactly how this thing works. After that, we'll uncover the one big flaw that kept it grounded on Earth and the really clever solution engineers came up with. And finally, we'll look at what the future might hold for this old but new powerhouse technology. First up, let's just take a moment to appreciate the incredible history here. This isn't some brand new, unproven concept we're talking about. This is a technology that was forged in the most demanding situation you can possibly imagine. The story actually goes way back, all the way to the 1930s with the early work of F.T. Bacon. By 1952, they had a working 5-kilowatt unit up and running. That's enough to power a small house. But its big moment, its time to shine, came in 1960, when NASA picked it for the Apollo program. And that legacy just kept going for decades, providing essential power for the Space Shuttle orbiter missions too. Okay, so how does this moonshot technology actually make power? Let's take a look inside the engine. At its heart, an alkaline fuel cell is actually pretty simple. It's got 3 key parts: a negative electrode called the anode, a positive one called the cathode, and then kind of stuck right in the middle is the electrolyte. In this case, it's a liquid solution of potassium hydroxide, or KOH. And these 3 simple parts work together to create a really powerful and incredibly clean chemical reaction. Probably the easiest way to picture this is to think of it like an electron bucket brigade. Okay, so it all starts over at the positive cathode. Oxygen from the air comes in, mixes with some water, and grabs electrons from the circuit. When it does that, it creates these things called hydroxide ions. Now, just think of these ions as little buckets, and each one is carrying a negative charge. They travel across the electrolyte over to the negative anode. There, they finally meet the hydrogen fuel, react with it, and here's the magic, they dump off their electrons into the circuit, creating an electric current. And for all you chemistry fans out there, this slide breaks it all down. You can see the specific reactions happening at the anode and the cathode. But honestly, the most important part is that overall reaction at the bottom. You put in hydrogen and oxygen, and the only things that come out are pure water, electricity, and a bit of heat. That is it. No carbon emissions, no pollutants. Incredibly clean. Now, this all sounds amazing, doesn't it? I mean, a proven, super efficient, clean power source. So you've got to be asking the question, if it's so great, why isn't this technology everywhere? Well, it turns out the AFC had a really serious weakness when it was brought down from space and back to Earth. The problem, it turns out, is something that is literally all around us: carbon dioxide. Now, in the pure oxygen environment of a spacecraft, this is a total non-issue. But here on Earth, our air has about 400 parts per million of CO2. And that might not sound like a lot, but for the original AFC design, it was a killer. See, when CO2 from the air gets inside the cell, it reacts with that potassium hydroxide electrolyte, and it creates a solid called potassium carbonate. And this is a complete disaster for the fuel cell. It gets rid of our charge-carrying buckets, it gums up the electrolyte, making it harder for anything to move, and worst of all, the solid bits literally clog the pores of the electrodes, choking the cell and just crippling its performance. And look, this isn't some tiny little effect. This graph says it all. The top line shows the cell's performance with CO2-free air. Yeah, it degrades, but pretty slowly. Now look at the bottom line. That's the same cell using regular air. The performance just falls off a cliff. This CO2 sensitivity was the Achilles heel that basically sidelined AFCs for any use on Earth for years. But of course, the story doesn't end there. Engineers are a clever bunch, and they came up with a brilliant fix that didn't just solve the CO2 problem, but it also added a whole bunch of other benefits. The big idea was to completely rethink how the electrolyte was managed. The original cells they used in space had an immobilized electrolyte. It was held in place, kind of like water in a sponge. In that design, any of those nasty carbonates that formed were just stuck there forever. The solution was to create a circulating electrolyte, where the liquid KOH is constantly flowing through the whole system. With a circulating system, any of those carbonate impurities just get washed away and filtered out externally, kind of like the oil filter in your car. But wait, it gets even better. This design also acts as its own cooling system, it stops the cell from drying out, and it even helps clear away gas bubbles from the electrodes, which makes the whole thing more efficient. It's just a really elegant, multi-purpose solution. So, with its biggest problem solved, the alkaline fuel cell is suddenly back in the game and making a serious comeback. Let's take a look at why it's so compelling for our energy future. Okay, let's talk numbers. The big one to remember here is 60%. That's the estimated higher heating value efficiency of an AFC running on pure hydrogen. That's basically just a measure of how much of the fuel's total energy gets turned into useful electricity. Now, to put that into perspective, other technologies like phosphoric acid fuel cells, they top out around 50%. So this thing is a fundamentally high-performance machine. But beyond just raw efficiency, AFCs have some other major advantages. Their performance, as we've seen, is excellent. But honestly, here's the real game changer: catalyst flexibility. A lot of other fuel cells need ridiculously expensive and rare platinum to work. AFCs can run on much cheaper, more common metals like nickel and silver. This is a huge deal. It gets rid of a massive cost barrier and frees the whole technology from relying on these volatile supply chains. Now, of course, it's not all perfect just yet. There are still some hurdles. This quote really gets to the heart of the final challenge, especially for things like stationary power plants. You know, a few thousand hours of life is totally fine for a space mission, but big utility-scale applications, they need to run for over 40,000 hours. We're talking almost 5 straight years of continuous operation to make any economic sense. So extending that operational lifetime is the next great engineering puzzle to solve. So, we're left with this fascinating question. We have this technology born in the space race, sidelined for decades because of one critical flaw, and now it's been redeemed through some really clever engineering. With its high efficiency and its potential for low-cost materials, could this 60-year-old design actually be a key piece of our clean energy future, powering everything from data centers to giant cargo ships? It's a powerful reminder that sometimes the best new ideas have been waiting for us all along.